to be the same. So analytical chemistry, chromatography. So let's actually figure out, or let's actually go through what is chromatography. So if you look at chromatography, normally we have a mobile phase. So solvent is going to be the mobile phase. So let's say we talk about paper chromatography. So you are going to actually put the paper, you will put the paper and then into a solvent. So there is solvent, and make sure that the baseline, this one, the solvent do not go through the baseline. So this one we already study. So the solvent, you have the solvent over here, and this is going to be the paper. Now what we need to know is going to be, under analytical chemistry you need to know these two terms, which is going to be the mobile phase, the mobile phase, and the term which is going to be stationary phase. So you have mobile phase and stationary phase. Now for chromatography, paper chromatography is going to be slightly different, because the mobile phase, is going to be the solvent, but the stationary phase, we always think that the stationary phase for paper chromatography is the paper, which is going to be the filter paper. We think like that, but it is not true. The filter paper, is just a physical component, but what they actually use is going to be the water that is trapped between the cellulose fiber of the filter paper. So the filter paper contains water molecules inside. That is the one that is going to be the stationary phase. This is not so important, but do remember when you explain for AS chemistry, for AS level, the mobile phase is going to be, it can be alcohol, it can be something, but the stationary phase, is not filter paper. Please remember that. The stationary phase is going to be the water molecules that is trapped into the cellulose fiber. It means there is liquid inside filter paper if you go in detail. So that is stationary phase. Now different substances, they have different affinity. Affinity means attraction, towards solvent and for water. Water is the stationary phase. Solvent is going to be the one that is going to be the mobile phase. So they have different affinity. Now based on this affinity, based on the interaction, you are going to have different rate of movement, over the filter paper. There is going to be, they will move differently. So we are going to use the RF value. What is RF value? Is the retardation factor. They are calculated. And this retardation factor, we have a database. It will be used for same temperature and the same solvent. And then you can compare. So colored substances can be seen directly. This one normally when you have paper chromatography, we actually see colored substances. You no need to add any chemicals. Like electrophoresis, they are last time we learned. You need to add chemicals in order to see. This one, paper chromatography, if you have colored substances, no need, they can be seen directly. But sometimes, you need to spray them using chemicals, where they are going to form colored compound on the chromatogram. For example, if you want to separate amino acids, so instead of using electrophoresis, you want to separate the amino acids. Then you are going to spray it using ninhydrin spray, or 9-hydrin spray. You are going to get bluish spot. So on the chromatogram, so it's going to be more advanced. But the next part you can see here. This is going to be the baseline. So normally, your mobile phase, or your solvent, should be below the baseline. And then you are the solvent, or the mobile phase, they will move up. The final part, when they move up, this is going to be known as the solvent front. Yeah, so you are going to actually measure. Okay, let's say you found something over here. This is going to be from the baseline to here. This is going to be X, and then you divide it by the Y value. You are going to get the RF value, retardation factor. Okay, do remember this RF value? I told you they have the database. Okay, depending on what solvent that you use, okay, they have the database and you can compare. Yeah, you can compare. Once you have a certain RF value, you want to find out, yeah, what is the compound. You can find out what is the compound, okay, using the RF value. But you need to make sure that you use the same solvent. You must make sure that you use the same temperature and the conditions. Yeah. Now, this one is not in your syllabus, okay, but it's included in your textbook. But since we already study about paper chromatography, let's actually study one way also. Yeah, sometimes, okay, we have what we call as two-way chromatography. Yeah, sometimes when you actually do the chromatography, the pigments, okay, when they are separated, they are going to overlap. Yeah, so when you have some kind of overlapping like this, what they do, they rotate the filter paper, yeah, at 90 degrees, 90 degrees, and they will actually calculate, yeah, they will run the sample again, yeah, and you are going to be able to separate, okay, the two solutes that are overlapping into different parts now. So that's why you can see when they do, yeah, they are going to be separated, okay, and then you will have something like this. Then you calculate, yeah, you calculate from the second solvent front. So this is what they call it two-way paper chromatography. Not so important, yeah, not so important. I just tell you it's a technique, yeah. This technique can be also used with thin layer chromatography. Later we'll see, yeah. So this one, okay, one or two more components, okay, they have similar RF value. Sometimes the spot will overlap and it will give you a poor separation. So you just need to rotate 90 degrees and rerun into in a different solvent. Yeah. So you just do the lazy job lah. So basically, rather than preparing another chromatography setup using filter paper, okay, so you just use something that you already used before and then try to rerun it using different sample. It's like if I put it in a different way, like you have a piece of paper, okay, and you wrote something, okay, after you finish writing something, you feel that the story that you wrote is terrible, yeah, and your handwriting is so terrible. If you submit, you get D, yeah. So what you decided, you just turn over, flip to the next page, and then, okay, the other page, you don't want to waste paper, you use the same page, and at the back of the page you write the new story, you change a little bit, yeah, and then we change your writing, yeah, and then you will submit. So that's going to be, maybe hopefully you get A. This is what they call it as two-way paper chromatograph. But in this case, two-way paper chromatography, they rotate the paper to 90 degrees, okay, but the other one, yeah, the paper, yeah, you flip it, yeah. So that will actually give you an idea about, okay, two-way paper chromatography. Let's not waste time with this. Okay, let's actually move on. Partition coefficients we have already learned under last time, okay, but under further I think reversible reactions, yeah. Okay, under that, okay, we have learned partition coefficients, yeah. So solute, okay, between, okay, it's going to be whenever you have solute between two solvents, yeah, we can use the partition coefficient, yeah. So in paper chromatography, there will be different partition coefficient corresponding to relative solubility between the two solvents, yeah. The mobile phase, okay, is the solvent chosen. Yeah, the other solvent is the solvent trapped in the paper structure. This one is the water, yeah, within the cellulose fiber. Greater the relative solubility in the mobile phase, okay, the faster the rate of movement. Yeah, so it means that, okay, if let's say whatever sample, yeah, that we want to separate, if they are going to be soluble more in the mobile phase, of course they will be transferred further. Yeah, but sometimes, okay, sometimes you do have, okay, whatever sample or the solute that we use, they get bonded, okay, to the stationary phase better, greater interaction. Yeah, let's say for example, polar molecules, okay, they can form great attraction towards water, which is the hydrogen bonding. Then if you compare polar and non-polar, okay, normally the polar will not go further up, okay, and then the non-polar will go further up. Why? Because non-polar do not get attached to the water. Yeah, so it depends on the interaction between the mobile phase and the stationary phase. Yeah, so it depends on that. Okay, so here, okay, this one is going to be just a revision. Yeah, you should know how to do this. Okay, you just look at this paper chromatogram, and then if the solvent used was ethanol, which sample ABC has the greatest solubility in ethanol. So if it is ethanol, okay, you use, okay, as a solvent, okay, let me check. Nathan, is ethanol mobile phase or is it going to be stationary phase?
Mobile, sir.
Yeah, it is mobile. Yeah, ethanol is a mobile phase. So if you're using ethanol as a mobile phase, okay, so which one should be the one that has the greatest solubility? Yeah, should be travel further. Yeah, should be travel further. So the answer is C. Okay, the answer is C. Now, if I change this question, yeah, which of the following has the greatest, okay, interaction towards water in the paper chromatography, in the paper, yeah, or which one has the greatest interaction with the stationary phase? The answer is B. Yeah, the answer is B, because they are going to be attached more, yeah, towards the stationary phase until they don't want to move. Yeah, they just stick, and then I don't want to leave. They don't want to leave. Yeah, the paper chromatogram. It means the stationary phase. So they are not going to be traveling further. So this one, okay, B, if they ask you, which one has maybe a greater interaction or bonding towards water in the stationary phase or something like that, then the answer is B. Yeah, so work out the RF value. This one is quite simple. The RF value, okay, if let's say you want to calculate for C, so this is going to be the X, okay, then divided by Y, you can calculate. Yeah, please this one we don't need to worry about it now. So let's actually go to our main stuff that we need to know for A2. Just now was AS, just a little bit of introduction, yeah, but this is the real deal. Yeah, so you have, okay, under this chapter, yeah, you have two chromatography, okay, apart from paper chromatography that you need to learn, which is thin layer chromatography, which is TLC. Yeah, so of course, okay, if it is thin layer, let's see what actually thin layer chromatography, what makes it different than paper chromatography. Yeah, so the first thing that you need to know about any particular chromatography is to find out, okay, or to list out the stationary phase and the mobile phase. Yeah, so you see the stationary phase is a solid. Yeah, so you see what is the difference, okay, with the paper chromatography. The stationary phase for paper chromatography is not solid, okay, because some students, they think that the filter paper is solid. Yeah, the answer is okay. The stationary phase in paper chromatography is water trapped in cellulose fiber of the filter paper. Okay, so they are technically not solid. But this one, yeah, thin layer chromatography, the stationary phase is solid. Okay, and this solid absorbs solute molecules onto its surface. This is going to be the same function as your paper chromatography also. So if you look at the stationary phase and the mobile phase, okay, so let's actually look into that. The stationary phase must memorize, yeah, it is going to be alumina, yeah, alumina or Al2O3, yeah, or silica, yeah, but when I check your syllabus, they didn't mention about silica, but I just leave it over there because in your textbook. Okay, but the idea is, okay, you are going to have alumina. Yeah, alumina is solid. Okay, so it's a solid stationary phase like what they did. Okay, but you cannot just simply put the alumina. You need to have a solid support. Okay, so what is a solid support? Yeah, so basically they will hold, okay, the stationary phase. Okay, they will hold the stationary phase. Something like your filter paper. Your filter paper is holding the water, yeah, of the stationary phase. So in this case, there will be a solid support that will be holding the alumina. Yeah. So let's actually look into the mobile phase. The mobile phase, okay, you can either use polar or non-polar solvent. Okay. So you can use any polar or non-polar solvent. So how thin layer chromatography is made? Yeah, it is made, okay, by taking the alumina, yeah, and mix it with water, yeah, and they say slurry, yeah, make it into a slurry and spread onto a microscope slide. Yeah, so it means it must be thin. Yeah, it must be very thin. So you need to actually mix it with water. Yeah, and then spread onto a microscope slide. And then, yeah, like something like cooking now. Yeah, you put it into oven. Yeah, why you need to put into the oven? You want to actually make it into solid. Yeah, you don't want the water to be, the liquid to be remaining. Yeah, so it dries out, okay, into a solid. Yeah, a white coating will be formed on the glass. Yeah, so Frederick, okay, remember just now stationary phase, I mentioned alumina on a solid support. Okay, can you tell me what is the solid support that we use over here, Frederick?
A paper similar to chromatogram?
No, the answer is already here. Microscope slide. The slide itself, okay, the glass slide itself is the solid support. Okay, so it means that when you put this microscope slide over there, okay, the glass, and you made the slurry of alumina, yeah, mixed with water, and then you actually put it into oven, you are going to actually have like a thin layer of a white, stationary phase alumina on top. So it means that you have a stationary phase on top of the glass support, which is going to be the microscope slide. That is what they mentioned, solid stationary space on solid support. This is going to be for this case, yeah, for this case. So you need to use the microscope slide over here. Okay, so the chromatogram is made similar way as paper chromatography. So for now, in your paper chromatography, okay, we have filter paper. Okay, but now in thin layer chromatography, you don't have filter paper. You have the microscope slide, okay, where you have a white coat of alumina, yeah, which is going to be a solid stationary phase on top of solid support. This is going to be something that you need to remember. Paper chromatography, you will have a liquid stationary phase okay, on top of a solid support, which is the filter paper. Yeah, so that's the difference. Yeah, so if you can look at it in that way. So if you look over here, okay, the absorption chromatography, the mobile phase, okay, moves over the stationary solid phase. Okay, remember just now I told you, you just put the glass slide over there. Okay, you have the glass slide, okay, or the microscope slide. Okay, so once you have the microscope slide, okay, then you have a solid surface over there, which is going to be the aluminum. Yeah, so the aluminum is on top, yeah, which is going to be your stationary phase. And then the solid molecule, the solute that you want to separate, okay, they are going to be absorbed on the surface of the stationary phase. Do take note the term. Okay, absorb means they stick to the surface. Absorb means they move within, yeah, from here to here. That is absorb. This is absorb. So it means that if you have Al2O3, if let's say the solute that has a greater attraction towards Al2O3, they will stay, okay, at the bottom. Like for example, this, okay, you can see this one is staying at the bottom. It means that, okay, the red color pigment, okay, they are attracted very or absorbed very strongly, okay, with the Al2O3, or in simple terms, they are going to have a greater interaction with the stationary phase. Yeah, that is going to be one of it. Okay, now that is actually with the stationary phase. Yeah, so you see, this one is not in your syllabus, so just can ignore. Yeah, so aluminum. Yeah, so you can see how separation is being made. Okay, so TLC, thin layer chromatography. Yeah, so polar molecules, okay, polar molecules, they have greater attraction to the polar solid because we are using Al2O3. This is polar. So polar, okay, they are going to be attracted to polar molecules because of the permanent dipole-dipole bonding. Okay, so they are going to be absorbed more strongly. Okay, so I can say that this particular pigment is more polar, okay, compared to this particular pigment. This is going to be less polar. So there are certain conclusions, yeah, that you can make, okay, using the separation. Yeah, so polar and less polar, and you see here they travel more slowly up. Yeah, why? Because they have greater attraction. Okay, they travel slowly up the thin layer because they are not going to they are attracted, okay, towards, they are absorbed towards the stationary phase. They don't want to move. Yeah, so solutes are identified by calculating the RF value. So in the end, yeah, it depends on the interaction with the stationary phase. But I think we didn't talk so much about the solubility to the mobile phase, but it depends on the solubility to the mobile phase as well. Okay, whether, because the mobile phase that we use, okay, they are going to be, okay, the mobile phase for thin layer chromatography, it can be also polar and non-polar. So let's say, okay, our solute, okay, they dissolve, it's a polar molecule. Of course, they are going to be, let's say the mobile phase is a polar molecule also. They dissolve well. Yeah, if polar dissolve well, so of course the polar molecule will actually be traveling more because they will move together with the mobile phase. Yeah, so it depends also on the attraction towards the mobile phase also. Yeah, so please take note. Yeah, so there are two. Yeah, it depends on the interaction with stationary phase and the relative solubility to the mobile phase. Yeah, so that is TLC. So TLC is normally described as adsorption chromatography. So normally they look into the attachment, okay, towards the stationary phase, which is going to be with the Al2O3. Yeah, some partitioning happens, okay, if water is present. So sometimes, okay, you know, the thin layer chromatography, you actually made it into you know, the when you prepare, you made it into slurry, yeah, so with water. So therefore they say that if you have water, then there will be some effect, yeah. They say that the partitioning can happen. Okay, so both dry alumina and silica can become rehydrated. It means, let's say you have water, yeah, so the dried, the dried stationary phase, okay, the one that you put into the oven, yeah, so they are going to actually become rehydrated. When this happens, water now, okay, is also going to become, okay, a stationary phase. This is going to be the reason why you have partitioning, okay, because we supposed to have only one stationary phase, which is going to be the Al2O3. But now if you have water, yeah, they will compete. Okay, they will say that, okay, stationary phase, yeah, is Al2O3. Our stationary phase can be also water. So they are going to get confused. Yeah, the attraction, some of it will go to water, some of it will absorb to solid space. So you will have a mixture of results that is going to be partitioning. Yeah, so anyway, okay, that is going to be one situation. Yeah, if you have water, we don't want to have water. Yeah, so anyway, why TLC is favored over paper chromatography? This is important. Why we need to actually have a glass slide, then we put it into oven, and then we need to use TLC and so on. Okay, the reason is TLC is faster. Okay, it is faster, okay, compared to paper chromatography. Yeah, you no need to wait for a very long time, and it can be used for a smaller sample. So normally we use it in forensic science. Yeah, and for example, okay, if you want to detect cannabis, yeah, so if you want to detect cannabis, okay, so what you can do, you can actually modify the thin layer chromatography, okay, into certain modification. Okay, the stationary phase, okay, we are going to use silica, yeah, similar like just now, alumina and silica. So silica is going to be SiO2. Okay, you spray with silver nitrate solution. Just now we use water, yeah, for normal situation, yeah, Al2O3, you add with water, you dry. But this one is silica sprayed with silver nitrate solution, and then you dry them, yeah. And then the mobile phase, okay, we didn't discuss the mobile phase. They say that just polar or non-polar it will do. But in this case, if you want to find out whether the sample contains cannabis, yeah, you can actually use methyl benzene as a mobile phase. And you know by now, now you know what is methyl benzene. Maybe last time when I teach you about methyl benzene, what is methyl benzene? Okay, so now it's going to be methyl benzene. Last time we used to say organic solvent. Yeah, so now we no need to use the term organic solvent. The term you can straight away say we will use methyl benzene. So this is going to be example for cannabis, yeah, to measure, to find out, okay, or separate, okay, the sample for cannabis. So you can read, yeah, you can read, okay. So TLC, okay, can separate what mechanism? Adsorption, yeah. So a mixture was separated using alumina. What substance you expect to rise further up? So you see propanon, okay, propanon, and you have hexane. Now hexane is non-polar, okay. Propanon is polar, okay. Stationary phase is going to be Al2O3, yeah, which is going to be polar, okay. Which one is going to be attracted more towards Al2O3, Josh? Which one is attracted more? Always remember polar with polar, non-polar with non-polar. Yeah, PDD, yeah, permanent dipole-dipole. Okay, and then van der Waals forces. Yeah, so if you look at it, okay, the polar molecules, okay, the polar molecule over here is going to be propanon. So propanon, okay, will be attracted, okay, more towards Al2O3. It means that, okay, the adsorption is greater for propanon. If the adsorption is greater for propanol, which is going to be a stationary phase, So stationary phase, okay, is the one that is going to be the glass within the slide. So it means that if they have greater attraction, they are not going to move up. So they will stay at the bottom. So if I have a sample, so propanol will stay at the bottom. Okay, hexane will go to the top. Okay, so I hope you can understand this. Okay, so you can actually go through this. Okay, hexane will rise up furthest. Okay, because okay, it has greater affinity for non-polar. So you see, methyl benzene also is going to be non-polar mobile phase. So hexane is non-polar. So hexane is also attracted more, okay, towards methyl benzene. So methyl benzene is the mobile phase. They will carry the hexane more. Yeah, so you can actually explain using these two. In the end, okay, it just comes down to whatever it is, okay, it depends on the interaction with the stationary phase and the relative solubility to the mobile phase. Okay, so in the end, you still come back to this. Okay, is that clear, Josh?
Yes, sir.
Okay. Now, so let's move on, okay, to gas liquid chromatography. So I forgot to put number 2 there. So there are 2, yeah, so we have done 1. So now we go for number 2. So for gas liquid chromatography, we call it as GLC, yeah. Before we go on, okay, you can see here, okay, I put over here, okay, TLC, yeah, thin layer chromatography. Mobile phase, what is the mobile phase? Okay, MP, mobile phase is a solvent. It can be either polar, okay, or it can be non-polar. Okay, some example, if you want to make for cannabis, then you use methyl benzene as the mobile phase. Okay, and then SP is a stationary phase. You can use alumina in your syllabus. Is alumina. You can forget about this. Okay, but for cannabis, yeah, you use silica, and then you spray with silver nitrate. Yeah, but for normal situation, you just need to slur, make it a slur, okay, alumina with water, then you put it into the oven. And then the support must be the solid support, so you use the microscope slide, yeah, something like that. Okay, but now, okay, for gas liquid chromatography, let's actually look at the difference. Okay, so the first thing is the sample, yeah, the sample must be, okay, made into gas. Yeah, the sample, that doesn't mean you can only separate gas. Yeah, so they say that whatever sample, okay, whether you have a gas sample, liquid sample, or solid sample, you change them into becoming gas. Okay, you have to change them into gas, and then you will pass through this gas into a column. Yeah, and the column contains, okay, stationary phase, and the sample is moved through by a inert carrier gas. From this term, when something is moved through by inert carrier gas, you know that this is the mobile phase. Okay, so mobile phase is a gas, okay, not liquid. Yeah, so if you put it together here, stationary phase, okay, can the high boiling non-polar liquid on solid support. So it means, okay, the important thing is it is non-polar liquid. Okay, non-polar liquid on solid support. Okay, remember earlier for TLC is going to be solid on solid support. Okay, but now liquid on solid support. Okay, and then the mobile phase, okay, is going to be inert carrier gas. So inert gas or unreactive gas. Yeah, this is very important. Okay, just now, okay, your mobile phase for TLC is going to be either polar or non-polar. Yeah, so it can be methyl benzene and so on. Okay, but this one is going to be gas, is going to be chromatography. So you see, the reason why they use the term gas liquid chromatography is because gas, okay, you need to use gas. Okay, you need to use gas sample, and then, okay, and then you are going to actually use, okay, the mobile phase also going to be gas, and you are going to move, okay, through a column that contains, okay, liquid, okay, as your stationary phase. Yeah, so that's why it's called gas liquid. Yeah, gas liquid chromatography. So all conditions must be controlled to make comparisons similar to your paper chromatography, similar to thin layer chromatography. Okay, depending on the what gas that you use, okay, you will have your own database. So you must use the same carrier gas. Okay, if it is inert, I cannot actually use neon, then suddenly replace with argon. Yeah, so different gas, okay, different carrier gas will have different results. Okay, so you need to make sure they have the same flow rate. You must make sure that they have the same stationary phase and the temperature. Then only you can compare. Yeah, the detector records the retention time. So they are not going to actually measure, the RF value. No, they are going to actually measure the time, okay, that the sample is inside the machine, or how long it takes, okay, to pass through the column. Yeah, the column is actually the liquid. Yeah, liquid on the solid support. So you are talking about how long it takes to pass through stationary phase. This is going to be in simple term. Yeah, based on the interaction with the stationary phase. This is the only interaction that will happen. Why? Because the mobile phase is unreactive or inert. Remember, for thin layer chromatography, okay, we have the interaction for both stationary phase and the solubility to mobile phase. But now, okay, you only have stationary phase. What is the reason? The reason is, okay, the mobile phase is going to be inert. Okay, the gas is inert. So you don't actually have any interaction with the mobile phase. So the mobile phase is just going to push the gas. Okay, it's just going to create a pressure to push the movement of the gas to pass through the column. So depending on the interaction, okay, of the gas, okay, the one that is moving, yeah, the gas from the solid, liquid, or the solid, liquid, or gas, okay, whatever sample, yeah, it's going to be pushed by the inert gas, okay. Depending on those gases, if they have interaction with the liquid stationary phase, then they are going to take a longer time. Okay, but if they don't have any interaction, yeah, towards the liquid, yeah, so they will pass through very quickly. Yeah, so the retention time is going to be less. So if you have, okay, greater retention time, okay, the time taken is more, okay, it means that, okay, there is going to be more interaction with the liquid in the stationary phase. Yeah, so that is going to be the explanation to it. Yeah, so greater time, retention time. Yeah, we will look into retention time. So this is going to be a diagram, but I don't think so you can visualize just by looking this. Yeah, so we'll skip. So you are going to get, okay, a graph like this. Yeah, so you don't need to plot the graph. Okay, the detector will actually detect and give you the graph and separate them. And using the graph, yeah, you can actually identify, okay, all these components inside the sample. This one is which, and so on. Okay, so depending on the retention time. Okay, but there are going to be certain limitations. Yeah, what are the limitations of gas liquid chromatography? They will have similar compounds, they have similar retention time. Okay, in this case, you see the retention time of this and this is very, very close. So I cannot say this is epoxy, ethane, or propanol. Okay, because they are quite close with each other. Okay, so that's the idea. Yeah, retention time is going to be very small. And sometimes if you want to use the gas liquid chromatography, some of the newly discovered compound, yeah, will not have a match in database. So you cannot actually use GLC to find new samples, or to, let's say, it's a new discovery. then you will not be able to detect any new discovery. So how do we use this gas chromatogram? So do remember different, like for example paper chromatography. Paper chromatography, we call it chromatogram. So paper chromatogram. Electrophoresis, electroferrogram, if you remember. Electroferrogram. For this one, we call it a gas chromatogram. Gas chromatogram. So thin layer chromatogram. A gas chromatogram, a thin layer chromatogram. So determination of the percentage composition of mixture by GLC. Now, if you put a sample, the sample might contain maybe you see 1, 2, 3, 4, 5, 6 compounds. So you can actually find out in this sample how many percentage is going to be pentan to on, how many percentage is heptane, and so on. So you can find out the percentages. You can find out the percentages, but you need to calculate. You need to calculate. So the normally now, the software will calculate for us. But the idea is, if you want to calculate manually also. The idea is, you need to find out the component peak. So for example, let's say I'm going to ignore this. I just use these two. You identify the component peak. So this is a component peak. These two are the component peak. So let's say I'm just going to use this as an example. So you identify the peak, then the area of each is measured. Now, how do I measure the area? Using your maths, it will form a triangle. So similar, the idea is you are going to measure using the formula for triangle. What is the formula of triangle? I think everyone should know. Half times the height times the base. So you can calculate. So you see, you can put you can find out the area, approximately. So GLC, using the system, they will measure the area of the peak automatically, and they print the result with the chromatogram. If let's say the peak are narrow and similar base width, like something like this. So if like something like this, you see here, this one, if I want to actually form a triangle, is quite difficult, but they can still form a triangle. But you see, it's too small. It's too small until they appear to have a line only. So if like that, what will they do? They say that then the peak height only will be used. Instead of peak area, to determine the proportion of the components in the mixture. So sometimes we do that. We do that. So we just use the height. So you can calculate. You can calculate. So this one, I think they just put basically how to use. How to use this. So you want to calculate, you can just see. Basically to determine the area. So what are the uses of GLC? GLC, remember for TLC, one of the use is going to be the one that I mentioned is to detect for cannabis. How do you detect cannabis for TLC? You use the silver nitrate instead of water. You use silica. You spray with silver nitrate, then you put in oven. So and then the mobile phase is going to be methyl benzene. So you can actually separate for cannabis. But what are the uses for GLC? GLC is used because you see this you're separating into different components. So testing for steroids in spots. So you can use GLC. Testing for fuels used for in Formula One motor racing. Because certain components in the fuel is not allowed. Yeah, so you can actually test for the fuels. Yeah, medical diagnosis in analysis blood samples to determine percentage of dissolved oxygen, nitrogen, carbon dioxide, carbon monoxide in blood samples. And you can combine with mass spectrometry. Yeah, we have learned about mass spectrometry. Yeah, if you are not sure, please go and refer to AS. Yeah, how do you calculate or use mass spectroscopy? Yeah, which is going to be like isotope. Generally, we use it for isotope Cl35, Cl37. Okay, how do I actually calculate the relative isotopic mass? Yeah, so you can actually use mass spectrometry. Okay, so you can combine the use with GLC. Okay, so here the last part is going to be for GLC. Explain, yeah, how retention time is measured. Retention time is measured for GLC. Do remember, it's only interaction with the stationary phase. Yeah, what is the stationary phase? Liquid, okay, in the column. Okay, liquid in the column. So liquid in the solid support. Okay, so they are going to actually form interaction. Yeah, so you see retention time is measured, okay, on how long it takes to travel the stationary phase and be detected. Okay, and then how do you measure the area? Okay, the area gives you the relative proportion. Okay, and then what you can use, okay, if let's say it produces sharp peaks, yeah, so only one line, then you just need to use the height. Okay, so that's it. Yeah, that's it under for GLC. So can we have, okay, someone to summarize, okay, what we have learned today? So Audrey, can you actually summarize what we have learned today, Audrey?
The thin layer chromatography, and then we learned the gas liquid chromatography and the mobile phase and stationary phases, and how to compare the data.
Yes.
Um,
Okay. Good. So there are few things, okay, maybe you need to revise or go through again, which is going to be what is the mobile phase and what is the stationary phase. Okay, and I started to compare, okay, paper chromatography and so on. So if you look at it, yeah, the main thing that we need to learn is TLC and GLC. Okay, but I did compare with paper chromatography. Yeah, because you need to also know about paper chromatography. So I did a very good comparison over there. Now, what I want you to do as your submission, yeah, your reflection, okay, on this lesson is I want you to create a TikTok video, yeah, to compare, yeah, to compare thin layer chromatography and gas liquid chromatography. Okay, it's quite simple. Or you can choose, okay, to make two videos, yeah, two TikTok videos. If you don't want to compare, you want to make one TLC, another one just for GLC, up to you. Yeah, but if you can, okay, better is you do extra work to really list down, okay, what's the difference between TLC and GLC, and then you compare. That will be a better video. Yeah, that will be a better video, and you make it into a short video, okay, in TikTok. Yeah, so that will actually serve as your reflection for today's lesson. Yeah, it's 8:22. Yeah, we still have yeah, 8:23, 7 more minutes. Okay, I will put you guys, okay, into the breakout room for a while. Okay, and then, okay, once it's 8:30, then I will bring you back over here. Yeah, so it still gives you, yeah, some time to maybe discuss, but do remember this is going to be individual work. Yeah, so you there is no point, but if you want to discuss, you want to talk, it's okay. Yeah, so you can go to your breakout rooms. Arwen, are you still there? So Arwen, you were asking about explain the water partitioning again, yeah. So the water partitioning, yeah. So what happens? Okay, um, uh, okay. Let me actually try to see whether what you're asking me is correct. Yeah. So are you talking about the water partitioning happening in the thin layer chromatography? Okay, so it's like this. Okay, so Arwen, just imagine like this. Uh, okay, you are making a slide. Okay, with slurry, yeah, which is the combination of water and Al2O3. Yeah, so we want the solute, yeah, the one that is traveling to be absorbed, okay, towards the stationary phase. Yeah, we want it to absorb towards the Al2O3. But now, if you have water as a contaminant, yeah, as a contaminant over there, so what happens is you are going to have, instead of only one stationary phase, you are going to have two stationary phase. Just imagine, okay, in an exam, I give you two pieces of paper, yeah, two pieces of paper, okay, and then ask you to answer, but you just need one piece of paper only, yeah. So you don't know which one to choose. Yeah, it depends on which at the moment you like, you choose that one and you follow. Yeah. So here, okay, you are going to actually supposed to be, maybe the foolscap paper must have the school logo. And then I give in your exam, one is school logo, another one with a blank paper. So you choose, okay, don't know, it's not your fault. Yeah, it's not the solid fault. Okay, it can be absorbed either Al2O3 or it can be absorbed towards the water molecule. Okay, so it's not the fault. Yeah, so it's actually the different. Yeah, since you have different, when we measure the RF value, we will measure the RF value based on the on our based on Al2O3. Okay, we will measure over there. But okay, like for example, when I mark, maybe I mark, okay, using the foolscap paper, the school foolscap paper, and there is a certain way of marking. But when I saw the in a A4 paper, it's not lined properly. Yeah, so it's actually different format. Okay, so you might actually write in a messy way and so on. So similar in water, okay, they are going to be separated differently. So when I compare with my database, okay, my sample, let's say I supposed to know the sample is such, but I cannot identify. Why? Because partitioning had happened. Can you understand that, Arwen? Yeah. So the partitioning can happen. Doesn't mean always happen, but it can happen. So if that happens, yeah, it's because of water. Yeah, that is actually the explanation. That is not only affecting for TLC in that way. Sometimes, okay, you see when people test for cannabis and so on, some results have to be tested twice. Yeah, why tested twice? Because sometimes we don't detect the cannabis. Okay, but we really know that it's a cannabis. So sometimes they detect twice because why? Similar reason. If you do once, okay, you are spraying with silver nitrate. Okay, you are spraying with silver nitrate. You are using silica. Yeah. So and then you are using methyl benzene as the mobile phase. Yeah. So what happens? Okay, the silver nitrate. Okay, if you have extra silver nitrate, maybe there will be partitioning happening also. Yeah. So maybe the cannabis is partitioned differently. Yeah. Or if let's say you have contaminant, maybe water. Yeah, I don't think so. Cannabis is attracted towards water, but there will be different partitioning happen if you have different chemicals. So you need to rerun the sample again to find out whether there is cannabis or not. Yeah, that's the explanation. case there are going to be a difference in results because of that. Yeah. So I'll go to Benedict room. Yeah. Yes.
Sir,
Hello, sir.
sir, for the GLC,
Mhm.
the stationary phase is a non-polar liquid, right?
Yes. For
So
GLC is inert.
the stationary phase, right?
Yeah. No, sorry. The stationary phase, okay, is a liquid. Yeah. The liquid, is it non-polar? Let me check. Yeah.
It says in the slide, but I think you said it can either be polar or non-polar, right?
No. For GLC, it should be non-polar. Okay, non-polar liquid
Oh, okay.
solid support.
How does the gas like slow down in the column? Does it have to be non-polar or Jackson non-polar, that kind of thing?
No. You mean how does the again?
How does the gas, like the sample, have like a greater retention time? How does it slow down the column?
Okay, because okay, the column itself, uh, contains the liquid. Yeah. So let's say the gas, okay, they are going to actually the column is going to be it's like a particular gas. Okay, if you put a particular pressure, yeah, so of course the gas supposed to come out without, if let's say there is no interaction, they will come out very fast. Yeah, but if there is interaction within the column, yeah, the gas will take a slightly slower time, okay, to come out. Okay, in the end, okay, they are going to get absorbed over there. But for us to understand, maybe we think that the different time difference is too little, but the GLC can detect. Okay, the GLC can detect the retention time.
How does
What?
What
yeah,
is
so,
the interaction, sir?
yeah, what does the
Interaction means
Yes.
they are going to form bonds. Michelle.
Oh, so
So
it's not
interaction means
polar and
you see
non-polar.
the adsorption. Just now we learned about adsorption, right? So the bonds, let's say for example, now you are actually having non-polar liquid, right? Okay, non-polar liquid doesn't mean that they cannot form bonds. Yeah, they can form bonds van der Waals forces with forces of attraction. Yeah, so they can form bonds also. Yeah, so they become adsorbed. Okay, so interaction. That's the interaction.
So the interaction, like how do you differentiate? So is it like maybe more non-polar gases will have greater retention time?
Yes.
Oh,
Yes.
okay.
Yes, in this case, okay, depends on the mobile phase that you use. So in this case, it's a non-polar liquid, right? So the gases that is non-polar, okay, they will be the interaction will be more. So the retention time is going to be greater for non-polar molecules.
Okay, thanks, sir.
Okay. Yeah, thanks.
Okay, guys. Okay, so it's already 8:35. Yeah. Please go through this, okay, the PowerPoint and so on, then go through the reflection. The the submission is on this Friday. Yeah, so you just can actually submit on Friday. Tomorrow we will do some a worksheet and then continue with the lesson. Yeah, so our aim is to finish chemical and analytics by next week. Yeah, next week Friday. That's my plan. Yeah, so let's see how we can do. Then after that we can do the passive paper revision. Yeah, so that's it from me. Yeah, see you guys. Okay, bye.
Bye, sir.
Bye, sir.
Bye, sir.
Bye, sir.
See you.